Well, there's a number of actual visualizations that people use in practice, what we call the workhorse visualizations. You've seen all of these before. I mean, you're math and stats students. Some of you are doing graduate work. This isn't news to you. So I'm not going to be spending too much time talking about the ins and the outs of all of those. At the very least, you should know how to produce line charts, histograms, box plots, line graphs, bar charts, and scatter plots using R or Python or whatever software you use to do data analysis. In practice, you might not have heard about some of these things. It's okay. On the slides, I've given you plenty of information about the workhorse ones. What I want to spend a bit of time focusing on isn't so much like the specifics of each of these types of charts. As I've said, you've seen a histogram before. I want us to keep in mind what it is that we can get out of our visualizations. Here's a histogram of the number of hours that have been worked in a specific week. And you know how to read a histogram, like you know the category with the highest frequency tells us what answer is most frequent, basically. So at least the most frequent answer was between 10 and 20 hours. We have these little check marks here, these little rugs that tell us exactly where some of the values are found. So presumably 12, 14, 15, 16, all the way up to 20. And that's, you know, something we can get the information about the specific observations, not just the combined or aggregated observations. The vertical bars here could represent some measure of central tendency. In this case, one of them is the median, the other one is the mean. And you know that the mean is probably the one on the right because there are some high values that are pulling the mean to the side. So this is info you can read about, you can tell about this. If you look at the numbers, the mode here, if you wanted this distribution, which is about 11, what you're reading from this mode is that there's 11 observations, 11 people who reported working between 10 and 20 hours. But if I look at the little rugs, little combs here, I see 1, 2, 3, 4, 5, 6, 7. Only 7 dots. 7 dots, 11 that have reported. There isn't a mistake here. It just so happens that, you know, at least 2 people have reported the same hours for some of those. And so some of these check marks are basically representing more than one observation, which we would not be able to tell if we just had the rug, the comb diagram. Another thing to keep in mind when you read this, you need to keep on interpreting what you're seeing, what I've called the multiple eyes in previous sessions. These are the reported work hours in 1 week. What is the maximum number of hours you have ever worked in a week, either at school or at work? I mean, what is your average time spent on work or at school? For most of us, it will reside somewhere between, 30 and 40, combination of work and school. I have in the past, and I'm not proud of this, I'm just stating it as it is, I have in the past worked 60, 70, one time I even worked up to 80 hours a week. I had too many deadlines. Not happy about this. This happened like 3 times in my life. Now if you look at this diagram here where there's roughly speaking about 40 individuals, I have a fair number of people who work more than 40 hours and even 3 individuals who have worked more than 80 hours. In the multiple eye framework, you would look at this and say, what's going on here? Are these data entry errors? Is there something about the context that I don't understand? Well, I didn't tell you where these people came from. I just said here's 40 people, roughly speaking, who have reported their work hours. The reality of it is that this is actually from a fire station. So these are firefighters in one of the multiple fire stations in Ottawa, and firefighters have a different type of work schedule than regular people do. Very often they will work like 48 straight hours in a week. then they'll do a few regular shifts as well, and then they won't work for another week. And so it is not completely surprising that we see some people with many hours and some people with not that many hours in the station. Okay. This wouldn't be something that you would expect to see in a regular office, and it might be that these 90-hour weeks here probably need to be looked at. It looks as though something might be wrong here, potentially. But at least we have a possible explanation for what we're seeing. Okay? So it's not enough to be able to produce a histogram, you need to be able to make sense of it. Line charts, again, I won't tell you too much about this. This is something you've known how to do since high school. Right? So you can recognize how one variable varies in function of another one by plotting a line chart. Whenever we plot line charts, traditionally we have expected, and this is the way I've just described it, that the horizontal axis represents the independent variable, and that the vertical axis represents the response variable, the dependent variable. But it doesn't have to be that way at all. So be careful when you produce a line chart. People will assume that your horizontal axis actually controls or causes the response on the vertical axis. Scatter plots are basically, like line charts without actually joining the points together. You've seen this before. You might have seen, or you might have called this a point cloud or cloud of points. Once you have a scatter plot between two variables, well, there's nothing to stop you from basically having scatter plots between all pairs of variables in your data set. And that might give you the impression that you can then literally represent all of the variables simultaneously on a two-dimensional surface. And it's true such as it is. I mean, you're only ever going to be producing the plots of pairs, right? So if it turns out that there's a relationship between 3 or 4 or more variables, you will not be able to identify that necessarily from the scatter plot matrix. That's one problem. The second problem is that here we have the very ubiquitous iris data set. You've seen it before in your courses. I'm plotting 4 variables in a scatter plot matrix. It's compact, it's easy to parse, it's easy to read. We get, it makes sense. But the reality of the situation is that in most data sets, you're going to have a lot more than 4 variables. And if you try to plot too many variables in a scatter plot matrix, what's going to happen is that you're going to have basically a square filled with unreadable blobs. All of the points will overlap on top of one another and nothing will be readable. So even though in theory this allows you to plot all of the variables in your data set on a two-dimensional surface, we are not able to make sense of them because there's just too many of them. So be smart, be clever. If you need to produce visualizations, you probably don't want, even though you have the functionality for it, to have more than 4 or 5 variables in the same data set. One of the issues with scatter plots as well is that while the top half, or the top triangle, is basically a repeat of the information of the bottom triangle. So you're wasting space that you could use to produce more or to give us more information about the data set. So you could decide to replace either the bottom panels or the top panels by some other visualization. So here, instead of actually having the scatter plots, I'm going to plot the density curves. Well, it's been flipped, it's been transposed because the top part is the transpose of the bottom part, but you can get some information, and you can use some histograms or some density curves on the diagonal as well. So you're able to put together a lot of information about the data set and, well, display it into one chart. That's economical. You don't need many charts here to tell the story, and that might sound good, such as it is, but it isn't too difficult to go overboard, to step over the line, to try to cram so much information in your display that nobody can read this and make sense of it. In the world of statistics, data analysis, it is sometimes encouraged to try to be very dense, to produce a lot of information in as small a space as possible. In the multiple eye framework, which is the one I've told you about already, that is emphatically not the case. The chart like this is not actionable. You can't take it and use it to do anything. There is too much information. So much information that you're drowning in it, and you don't have the ability to draw insights that can be used. You are better off producing a number of charts, declutter them, make them easy to read and to understand, tie them together with a story, a narrative, than to try to put all of your information on one chart that nobody will be able to read. Okay, that's important. In this course, the focus is on explainability, understanding the situation. Nobody can explain or understand what's happening by looking at this monstrous chart. For your projects specifically, I don't want to see things like that. So this was for using visualizations for exploration, to try to get a sense, to try to build an intuition for the data set. But that's not the only reason we might want to use visualization. We can also use it at the end of the process once we want to communicate the results, once we want to communicate the insights. One of the shining lights of data visualization is Edward Tufte. He wrote a series of books over 20-some years which have really defined the field. He has a very interesting take on what makes good data visualizations. Why do we create data visualizations? Why do we try to visualize things? We're trying to reason and communicate our thoughts. Right? That's what we're trying to do. And so when you produce a chart, you are not just an independent producer of a chart. You're also a consumer of charts. Right? You might not consume the one that you've produced until you've produced it. That's conceivable. And it's different when you consume something you've produced yourself because you know what went into making the chart. But you are a consumer of other charts, other analyst charts. You do take in data visually from other sources. And there's a symmetry there. Whatever you put in your charts when you build them, when you produce them, should be what consumers of charts look for. Right? So it's ridiculous to live in a world where people either produce charts or look at charts. We have to assume that whenever you produce charts, you are also somebody who looks at charts. And we also have to assume, although that might require us to educate the audience, that whomever looks at our charts would also be able to produce charts, or at least would have a good understanding of what goes into producing a chart. And there's 6 items that he thinks we should be looking for in good visualization, 6 types of things. We should look for the ability to make meaningful comparisons between observations, between variables, between situations. We should also be able to highlight causality or causal networks. Now that's very difficult to do. Does tobacco cause cancer? Well, yes, I mean, tobacco causes cancer. That everybody knows that, right? Except the data that we have doesn't show that tobacco causes cancer. The data that we have eliminates other possibilities, not all the other possibilities, but a bunch of other possibilities, and it suggests that there might be a link between tobacco and cancer, but it doesn't show us that the link is causal. The causality bit doesn't come from data analysis or data visualization. It comes from other external proofs, medical proofs, which aren't necessarily the same as data proofs. Data analysis can only ever highlight associations, correlations. Well, there's a sub-branch of data analysis called causality analysis, and there it tries to do a little bit more. When we talk about Bayesian analysis in the next module, we'll be able to say more than just highlighting correlations. But for the time being, we'll take the position that in the best case scenario, when you analyze data, you highlight correlations. You show associations, but you don't show causes. So a good chart would be one that hints at potential causality relationships. It should also be able to highlight or showcase some structure in the data set that is not evident to analysts if all they do is look at the data set tables or the databases. Your good charts should be able to basically provide multivariate links. We are past the days where we could get by with univariate distributions or univariate descriptions or even bivariate descriptions. We have data sets that have 20, 50, 100,000 variables. They're going to be linked somehow. You need to try to show what the links are amongst multiple variables. Your data should be integrated and relevant. What that means, well, there's many things that this could mean. The first one is that make sure you label your charts properly so that people can actually parse and understand them. You don't just plop a bunch of markers with colors and hope that they're going to figure out what it means. But it also means that your data visualizations are part of the analysis. They are not relegated to the end notes or to the appendices. They provide backing for your assertions, analytically speaking, and they also drive or help you drive the narrative, how you're telling the story of the data set that you're analyzing or the situation that you're approaching. Two other items. Look, there should be honest documentation. Make the data available online, or help tell people how you ran the analysis that you're using to provide the visualization. Or if you had to remove observations, let it be known that you removed observations. Technically speaking, there isn't going to be an awful lot of room on the chart itself to provide that information. So your best bet would be to say, I'm producing a documentation package. Make it available online. I'll send the link. I'll add the link to my visualization so that people can go and add and take a look at what you've done. Dig deeper. Right? You're not just doing this for the ideal of being honest, you're also doing it to protect yourself, right? Once you've produced a visualization, you don't know where it's going to end up. If you've published it online, somebody else might take over it, take control of it, and make it say something other than what you've said. If you've kept track of your documentation, you can point back and say, no, this is what is actually being said here. Now, you don't want your visualizations to be used for, well, propaganda purposes. Finally, his big take is that the primary focus should be on the content of the visualization. Yes, it's important that you have pretty visualizations, that they're aesthetically pleasing. The graphic design element is useful. I mean, if you produce something which is appealing to people, they're more likely to take the chart seriously than if you produce something which is unappealing. But it cannot be the only driver. Your content and, in my opinion, the aesthetics are equally important. Okay? You cannot sacrifice content, however. You could sacrifice aesthetics if you had to, and hope that you have an audience which is willing to forgive you the sin of not having an appealing chart. There are also questions of accessibility. 20 years ago, this isn't something we cared about. Now we care about it substantially more. We used to. If you have a table of numbers, you can make that be accessible to visually impaired people by translating it in braille. And this little embossing for letters and numbers, and you can use your tactile senses to basically read the chart on paper. But that's not always going to be very easy to do for a chart. How would you translate a chart into an embossing? There are tactile tools that allow you to do that. We're not going to talk about not going to talk about these things here, but it's actually fairly expensive to get a tactile reader if you're visually impaired, and it's not always easy or obvious how you would translate specific things like color into a tactile sensor. One of the solutions here might be that you're trying to describe the features and the emerging structures that you can see in a chart. So if you're saying, for instance, that, oh, I'm seeing here that there's a linear trend between the amount of time you wait, the number of people who arrive at a counter to be served and how quickly they're being served, like in the example we saw in the last lecture. Like, all right, well, that's an easy one to spot. I'll say, oh, there's an outlier here. Tell me that this is an outlier. Great, fantastic. But for more complicated data sets with more complicated displays, the features are not always known or spotted by the analysts. We're going to see a chart soon, and every single time I see that chart again, I spot something else that I hadn't seen the last time I looked at it. Right? So if you want to describe everything that there is to be found in the chart, you need to know everything that there is to be found in the chart. For location of points, that's feasible. For color of points, that's feasible. But for emergent patterns, for insights, that's not usually possible. There's other tools that you can use. We should really call data visualization data perception. How do we perceive the data sets? And it turns out there's tons of different ways to do this. It is an accident of evolution that we use our visual sense to make sense of data. If we were a species that evolved without eyesight, well, we'd be using our other senses to make sense of data. And since we would have evolved with these other senses, or at least without sight, we would have figured out a way to really read data just as well without having to refer to our eyes. So we can imagine tactile or texture-based representation. There's text-to-speech possibilities as well. You can use sound, you can use music, sonifications if you want. You can even imagine an odor-based perception of data or a taste-based perception of data. I mean, it's harder to make sense of that because our sight is such a huge part of our understanding of the world. But if we didn't have sight, we would find some other way. Or species without sight that have evolved intelligence and technological capabilities somewhere in the universe would presumably be able to still make sense of the world around them, just they would be using a different set of senses. Okay, so we are limited by the data visualization framework, and we think that this is the only way to represent data. It doesn't harm us to try to incorporate other senses in our understanding of data. If you can think of it as an example of something of a similar nature, if you've grown up in Ottawa, and I'm sure wherever you grew up you might have seen something of a similar nature. When I was a child growing up in Ottawa, if you went on the bus to go places, we didn't have little panels with orange lighting telling you what stop I was getting at. Like, we were looking at where we were, and if we get to our stop, we rang the bell, and this is how we would get out. And I remember when they first added these panels, I thought, this is stupid. I can totally tell where I am. This is Herdman, this is Ottawa, this is wherever it was I was trying to get to. But eventually what I realized is that I could start reading, and all I'd have to do is take a quick look to see where I was. So I was able to read on the bus without worrying about missing my bus anymore. And it turns out that even though I was not deaf or visually impaired, because eventually they also added like a voice that read the name of the stuff. Even though I had access to all of my senses, I actually benefited from accessibility design by trying to reiterate or integrate other senses in the process. Well, you have to think the same way on the data representation, data perception, data visualization front. You might have heard of the term infographic as opposed to data visualization. We will separate between infographics and data visualization. We'll distinguish them. Sometimes an infographic is called for, sometimes data visualization is called for. Infographics usually really focus on the storytelling, the subjectivity. It is intended for a specific audience. It is self-contained and discrete. It contains all of the information you need to make sense of the data. You don't usually need a second, a third, a fourth, or a fifth infographic to be able to understand the purpose of the infographic. For infographics, the graphic design aspect is crucial. One of the drawbacks is that you can't usually reuse the infographic with another data set. It is a way to visualize a data set which is specific to the data set and the message that you're trying to carry. And it also usually incorporates information which is unquantifiable. A trick to know if you're dealing with an infographic or a data visualization, although it's not a 100% guaranteed trick, if you can't easily imagine what the underlying data set was that was used to create the visualization, you're probably working or dealing with an infographic instead of a data visualization. They have their purpose. They're not completely useless, but it is easier to mislead an audience using infographics through negligence. Here's an example of such an infographic. What is the data set that is used to build this? What's the purpose? What's the storytelling purpose? What's the message? Who is the audience? Give you a chance to answer that on your own. Compare that now to something like this. A data visualization. And here we use data visualization as a noun. This is an object, an item, a method. It is objective in the sense that it takes the data that you give it and it produces something. And if you were using the same method, or if somebody else was using the same method in the same data set, they would actually produce the same output. Deterministic in a sense. It focuses on things that are quantifiable. It does make the data set accessible, right? You can think of data visualizations as a way to reduce a large data set into a smaller format, which carries, roughly speaking, the same amount of information. In Module 4, we will talk about feature selection and dimension reduction, while data visualization is usually one of the unspoken ways of doing dimension reduction. You're probably dealing with a data visualization if it is possible to automate the process. If you can apply the method to a different data set and still get something that makes sense, you're probably dealing with a data visualization. In this example that we have here, the units, the observations are the 50 American states. And this one is telling us something about the wealth and the population of each of the states. And, of the various regions in which the states are found. While you can imagine producing a different visualization using a different data set, but that would maintain the spirit of this if you were using Canadian provinces, European countries, African countries, Chinese regions or provinces. Right? All of that would basically give you, it'd be a different chart because we're feeding them a different data set, but we wouldn't need to sort of reinvent a whole new method for these other data sets. That's the hallmark of a data visualization. We can also fairly easily imagine what data set went into producing this visualization. Here, I literally have to have a list of states, the regions in which the states are, or the subregions, the regions in which the subregions are, a population for the state, a population, and a median income, median household income for the states, and then I can create this visualization. That's all I need. So if you can imagine fairly easily what data set went underneath, you probably are dealing with a data visualization. If they can be generated automatically, probably a data visualization. If the look and the feel don't seem to be as much to the front as the insights and the content, probably a data visualization. If you're able to question the validity of the visualization, you're probably dealing with a visualization rather than infographic. And by that I mean question, basically there's a question mark. Something about the visualization doesn't strike you as being correct. It could be that what is at fault isn't the data visualization, but your understanding of the context. Your intuition might not be developed as much as it should have been. That's a possibility. In this example here, in this chart, the blue states, the blue regions, are meant to be the low-income states or regions, and the red states or orange states are the high-income region. And I don't know how much you know about the United States, its history, its culture, its regional variants. My understanding of the United States doesn't match with the visualization that I'm seeing here. If high-income states are red, I would expect to see states like New York State to be in orange-red, and states like Alabama to be in blue. That is not what I'm seeing here. I'm seeing Alabama in orange and New York State here in blue. So it's conceivable that the colors have been reversed. It's also conceivable that I'm not really understanding the states as well as I think I am. Median household income, it could easily be the case that there's various forms of income disparity in the states, and I don't understand that context, which makes me doubt or question the data visualization. But at any rate, whether I'm right or wrong about my questioning, the ability to raise questions and to figure out how you might answer them, that's also a hallmark of a data visualization. If you can't really ask questions or raise doubts, if you can't figure out how you would clarify the situation, what data set would be needed, then you're probably working with an infographic. In this course, we're going to focus on data visualizations, not on infographics. You might also see something that looks like this. We're going to talk about the actual fundamental principles here. This is a series of curves. This is just like scatter plots together with a line graph, and we've separated the data into various years by color. So the green points and line represent what's happening in 2012. In blue we have 1980, in red 1950, and in purple 1800. And we're plotting here the GDP per capita in 1990 adjusted dollars, horizontal axis, against the life expectancy. And when it's plotted like this, there's a few insights you can come to, right? You can actually see that it looks as though the GDP per capita is increasing over time. There are still countries in 2012 that don't have a very high GDP per capita, and there were countries in 1800 that had higher GDP per capita, but on average, as we move in time, the points are getting higher and further to the right. So people live longer and tend to be wealthier on average. They used to be. Another bit that you're getting out of this, presumably, if you're used to the x-axis representing the independent variable, the authors of this chart seem to be indicating that life expectancy is caused, or at least driven, by GDP per capita, by wealth. Except I don't know for a fact that this is the case. I suspect that it is the case. It makes more sense than the other way around, saying that how wealthy people are is driven by how long they live. Although you can imagine that people who live longer have a longer time span to accumulate wealth. You can also imagine that the longer you live, at some point you stop accumulating wealth because you're not working anymore. So the causality relationship isn't clear. Like, I suspect that it's the other way around. I think this is right. I think wealth typically leads you to having better health options, which typically leads you to living longer. But that's not necessarily the case. It's not too hard to imagine that some other factor, perhaps education, could drive both wealth and health. And that is not something that would be indicated in this chart. So even though it's presented to you as though one is a function of the other, it's not clearly the case that this is actually what's happening. Right? So you have to be careful about the meaning, the message that your charts are conveying, unbeknownst to you perhaps. And this is what we mean by saying that the producers should also put their consumer caps on to be able to see what it is that they've produced through the eyes of people who don't understand the data, who do not have the data with them to build a chart. Here's a chart using the same data, although it only uses the 2012 data. It doesn't look the same, right? I mean, we have what looks, roughly speaking, to be a straight line across here. Let's see how well I can make this visible. Whereas we didn't have a straight line at all. What we had in 2012 here, the green, was something which is said to be logarithmic. But if I didn't tell you it was logarithmic, you might not be able to recognize this as a logarithmic curve. Here, though, if I tell you that there's a, roughly speaking, a straight line fit, well, it's like, okay, we understand that this is a straight line fit. It makes sense. We can parse that. We can read it. Are we able to apply the fundamental principles to see if they've been applied, I should have said? Are we able to make meaningful comparisons? If I'm asking you whether the United States is a wealthier country than Japan, well, first of all, can you identify the United States? It's like, yeah, it's this one here. Can I identify Japan? Yeah, it's this one here. That's not difficult to tell. Are the United States wealthier than Japan? Well, this point here is further to the right. Hence, it is wealthier according to the income per capita measurement. And Japan, in exchange, would be healthier, a longer life expectancy. If I'm asking you to identify on this previous chart China, well, you can't. I mean, unless you happen to sit on the income, GDP per capita, and the life expectancy, any one of these points could be China. It's probably not one of those points, and it's probably not one of those points, but in this region here, any one of those could be China. But if I include another design element, which is the population of the country, then it is very easy to identify which one is China. It's got to be one of the two big bubbles. And if you know a little bit about geopolitical settings, you'd say, well, this has got to be China. On the income per person metric and on the life expectancy metric, China is doing better than India. And so the one further to the right and higher up has to be China. So it's easy to make comparisons. It's easy to find specific things. I've told you we can see underlying structures, good visualization. I have the straight line relationship between the logarithm of the income and the life expectancy. There's a few other things I can point out as well. Look, there's points here. 5 countries that don't seem to match the overall pattern. Well, you can also include Nigeria in there if you want it to be thorough, but definitely these 5 countries here don't seem to fit the rest of the picture, the equation. These outliers, well, the chart doesn't explain why they're outliers, but the fact that they're outliers makes you want to look into this deeper. One of those points is South Africa. I don't know how much you know about history, but South Africa is a country that practiced apartheid for years, segregating the African or descendant population and the black South African population. And so even though this is one bubble, one country, it really represents 2 rather heterogeneous groups that have different characteristics. And this is why you see the bubbles not being in the right place. This structure is not evident if you just look at a series of observations in a table. This chart doesn't prove that apartheid is what caused the bubbles here to be in a different position, but it makes you want to know more. So, what else can we say about this here? If you're going to be presenting analysis results, you're going to make sure your graphics are clear and engaging. This here might not necessarily be the way you would present the information, but it does give you a chart which is both clear and engaging. The thing is, so this chart here, this is also a clear and engaging chart. Not as engaging because it's harder to make sense of it. We don't have specific points, specific locations, as we would here. Here we can identify countries. We might even be able to identify our country, and that speaks to us, or the country of our partner, or the country where we study, or any of these other things. So amongst these 2 charts, while they both carry the same, convey the same, or carry the same informational content, one of them seems to be better at getting a point across. Well, there's a slight difference here. We have the passage of time, but you could literally go online and find this tool here and literally see what happens from year to year. And you can also incorporate the passage of time in this chart. Okay? For my money, this is a great multiple eye chart. It has great documentation as well if you ever want to read this up. Do you believe the numbers that are given, say for Canada, right about here? A certain income per person, a certain life expectancy. It's like, yeah, I probably believe it. These numbers probably come from ESDC or StatScan or some other organization that I have, faith in. But if I look at the numbers for, say, North Korea, which is right here, I don't know that I would have an easy time believing these numbers. They could very well be true, but how do they, the authors of this chart, how do they come up with numbers that trust? So I have a question on Slack that asks me how I would incorporate time in that chart. In that chart specifically, statically, I could not incorporate time. But if I created the same chart for various years, I would create a bubble chart, a snapshot at various time intervals, and then you could stitch them together into a movie. So there's a tool online. I'm going to be I'm posting a link on the Slack channel, gapminder.org/tools, that basically takes this chart and runs through 220 years worth of data. And you can see the passage of time and the effect that this would have. In particular, you will see on that chart that both China and India actually have momentum on their side. Like up until very recently, they were falling on the bottom left corner, but they're moving out of there very quickly, and they're overtaking the Western nations. At least when it comes to these two metrics. Okay, so animation is a tool that we now have that we didn't have before, and we can use that to incorporate, amongst other things, the passage of time. Okay, what method to use? Look, it depends. There's new methods that appear all the time. You may be able to get by with just scatter plots and histograms. Multiple such scatter plots and histograms, that's possible. I have more examples in the course notes. I have more examples using R in the notebooks. You can take a look at some of these things. What really matters is that you're conveying the message, conveying the insights that are found in the data. And you can use basically anything you want as long as you're able to convey these insights, convey the message, and to do so honestly. One thing to keep in mind when you create these charts is that the way we perceive visual input is fragmented. Our eyes are continuously scanning. They go in different locations, little jumps. When you think through your visual senses, you're looking for patterns. And there's two types of ways to look for patterns. You can use your pre-attentive processes. Everything that happens fast, instinctively, quickly, at a glance. The ability to gather information without really thinking about it. The features, the patterns, the objects. If I'm asking you to find the red dot in the upper image in blue, you find it easily, right? The color contrast is strong. Color as a contrast is basically a pre-attentive process if the colors have enough contrast to start with. But then you also have attentive processes, the processes that require you to sit down and to think about what you're seeing. If I'm asking you to find the red circle in the bottom chart, you cannot find it just as easily. Right? Because here the shapes don't provide you with enough contrast when the colors are the same throughout. So if you want the insights to be gleaned quickly, efficiently, you need to be able to call upon the pre-attentive processes of your audience. And if what you want is for them to sit down and to think and to spend a lot of time with the charts, then you'll be focusing on the attentive processes. Ideally, you have a mixture of both. Some insights are easily obtainable at a glance, and some insights take longer to obtain. You want to reward both a quick look and a second, a third, a fourth look. At least that's my position on these charts. So a good chart, a good visualization would be one that allows you to learn something new every time you look at it. I don't know if you're familiar with the Waldo books. You'd rather be in this situation, where there's a Waldo to be found and it's not that difficult to find it, than to be in this situation. Where is Waldo here? And you might need to spend a lot of time on this chart before you realize that there's no Waldo in there. There's no insight for you to be gleaned. Okay, so don't waste your time looking for Waldo. It's not there. But you don't know it's not there unless I tell you it's not there, because it could be there, because you can't tell easily if it's there or not. Right? So your insights, if they are there, should be easy to find. And if they're not easy to find, well, either you're not using the right visualization for the insight, or you need to describe how to find it in a better manner. You need to highlight it in a better manner. What are some basic rules that I want you to apply? Check the data. Look for outliers, look for spikes, look for anomalies. Is everything the way it should be, or are there any points, such as South Africa and that Gapminder map, that beg for an explanation? Explain the encoding. You can't assume that the readers will know what your encoding means. If you look at this chart here, can you make sense of it? I can make sense of it. I came up with this chart years ago. I knew exactly what I was doing with it. I had the data set, and I was speaking to an audience that would understand all of these things. But unless you worked in transportation circles, you will not recognize that daily VKT means daily vehicle kilometers traveled. How much distance each vehicle is traveling on a daily basis by vehicle type and vehicle age. I've labeled my categories. My turquoise and blues are passenger cars. The orange things are minivans. Pickup cargos are in green. SUVs are in, well, purplish shades. And then the age as well is given there. Right? Take the time to explain the encoding. You should label the axes. Knowing the scale is important. If I'm showing you an axis which is just a straight line, you don't know if this is meant to be a linear axis or a logarithmic axis, or some other weird axis. A straight line just looks like a straight line no matter how you produce it. So give me ticks, give me labels, give me values if you're going to have axes. Include the units. You should eliminate the need for guesswork. Your geometry should be kept in check. When you use area to represent a quantity, such as the population of a country represented by the bubble, are you able to tell easily, here for instance, that the population of China, based on this circle, is roughly 3.5 times or 3 times as big as the population of the United States based on this circle? No, human beings, we can't do that. We can tell that the population of China is bigger than that of the United States. By which factor? That's very hard for us to do, right? Include your sources. You're not doing it just to protect yourself, though you're doing it to let people dig deeper than they might want to. Here's a chart which basically shows you the relationship between eggplant consumption per week and cancer cases, both incidence and mortality. And from this chart, very strange chart, I mean, if you look at the axis here, it seems to be going the opposite way of what we would expect. But from this chart, we would conclude that it seems as though not eating eggplants would be beneficial to your chances of not dying from cancer. Right? And we know it's true, the chart says it. Well, is it? I don't like eggplant, so I made this chart to try to convince my wife as a joke that we shouldn't be eating eggplant. So it's a joke chart. There's nothing in there that's true. But it looks like it could be a real chart. And without any data or sources to back this up, you can imagine that somebody could take this and, post it online, and next thing you know, it's gone semi-viral. I'm not kidding myself. This chart would not go viral, but you can imagine a setup where it could. Once you've produced a chart, it is out of your hands. Once you've published it, you don't really control it anymore, even though you might want to control it. If you include your sources in the chart, people can double check to see if everything makes sense, or if you're just literally pulling their legs. Now, here I made this as a joke, but you can easily imagine organizations or people making charts not as a joke, but to attempt to mislead. And it is easy to mislead with visualizations because we have a bias towards trusting charts. When we look at charts, we assume that they've been built or made using data and that the data is objective and true. We believe data to be true, even though data could be faked and a chart could be faked. Include your sources, you protect yourself, you allow other people to dig deeper. And you should also consider your audience. If you're producing a poster, an infographic, you may afford to be wordy because you have the audience who's going to want to read stuff. If you're presenting results, presenting a chart, you probably want to stick with minimalist presentations. Less is more, as the English saying goes. As an exercise, you might want to revisit this chart. How does this visualization help the audience understand the data? Can you come up with other interesting patterns in there than what I've established, what I've discussed in a previous slide? What's really important is, can you get the point across? If the point isn't getting across, if you have to go and explain the point, then your visualization is not the right visualization. If you add design elements, you can enhance the understanding of the data. A suggestion for the project, and I think I might have explicitly stated this, you should try out a bunch of visualization. Don't just try to build two from scratch. Try a bunch of univariate visualization, bivariate visualizations. Try to come up with ways to incorporate 3 variables, 4 variables, and so forth. Pick specific methods with a design plan in mind. You're trying to show this. I think this visualization method would be best. Let me try it. But you should also try random methods with random variables without really thinking about whether they will be a good choice or not. Because you can also be blinded or biased by your understanding of the situation. And if you have biases that stop you from understanding the data set in its full, in a fuller capacity, well, you're always going to be presenting or preparing the same types of charts, and you'll never be able to break through this barrier to understanding. Insights or fuller insights will forever evade you. So I suggest that you also build random visualizations. Okay, what are some of the things you might actually see? Well, there's other types of charts. Now, I think you will have seen some of those before. If not, I'm just giving you a name, a quick example, a quick description of them. You'll figure out how to create those in R and in Python. You can take a look at the code that I've provided. There's going to be examples of a lot of these things. Heat maps. Heat maps are actually pretty useful if you're working with categorical data for your axes, and or you can have only one axis if you want, and potentially a numerical variable or a proportion for a third variable. So then the color can be used to determine the intensity of the value. And here, I mean, if I take off my glasses, for instance, and I try to figure out what these numbers are, I cannot see any of these numbers on my chart. But I see the colors, and I can easily tell that there's a darker color here. There seems to be a curve, darker points, something like this here as well, right? So heat maps basically use colors and color intensity to help you get a better sense of the data. Geographical maps can also be useful. We have an understanding of what the world looks like. At least if you show me an outline of the Americas or an outline of Eurasia or Africa, I recognize what they are. And it can be provided in different projections. Like you can imagine a map where you, rather than using the Atlantic as your center point, you'll use the Pacific at the center point. And you can imagine a map where it's a polar projection, either Arctic or Antarctic projections. And you can imagine many different ways to project this sphere onto a two-dimensional flat surface. But even when they're distorted by projections, we've seen enough maps to fully understand where we stand, where the map is. So if you produce maps where one of the values will help you deform the map. So a country is like shrunk if it doesn't, if the value of some variable is smaller than it should be, we can easily tell at a glance that, say, a country is not performing as it should. Or if you deform it based on other things. So here we're looking at this other map. And what we're seeing is China, for instance, roughly speaking has, not quite, but roughly speaking has the shape that we would expect and the size that we would expect. Canada is much smaller than we would expect to see on a map. The United States are bloated, much bigger. Same thing with the UK and Germany. And there's a color element that goes with this that basically seems to indicate the degree with which the map has been deformed. And that gives us a bit of an idea as to what values are larger than they should be based on, well, a number of different factors. Okay, so that could be a useful way to provide information. One of my personal favorite types of charts is the bubble chart. You can think of the bubble chart as a scatter plot on steroids. You have two variables, x and y, for instance. Could be numerical. They don't have to be numerical, as long as they're ordered. Makes sense. You can imagine ordered categorical variables could also be used for the axes. And then you have variables that are mapped to the shape of the marker, the size of the marker, the color of the marker, like we had for the Gapminder chart. You can get a lot of information for that. This specific example here of a bubble chart is a poor example of a bubble chart. The background should not be blue. Background doesn't provide me with enough contrast. I can't really read the text. This could be made substantially more appealing and easier to read through decluttering techniques. But it provides me with some information. For instance, I am seeing that there's 4 players on that team which don't really seem to fit in with the other players. Their performance is different somehow than what one would expect. So that's not a bad chart this way. Okay, so bubble charts are good. They do allow you to put together a lot of information. It's easy to see insights. This is a chart which is substantially less cluttered. It's also a bubble chart. We have the title for it, Abundance of Chemical Elements. And so we have 3 variables. Horizontally, it's their abundance in the universe. Vertically, it's the abundance in the Earth's crust. And the size of the bubble tells you something about the abundance in human beings. It's all relative abundances here. So the elements that are very abundant in the universe would be further to the right. The elements that are abundant in the Earth's crust would be higher up. And the elements that are very abundant in human beings would be bigger. And so we see something like oxygen, hydrogen, carbon, nitrogen, 4 building blocks of life. Well, there's more than these 4, obviously. Now, if you're looking at this, though, you may be wondering, oh, hang on. Something is missing. Where's helium in this? Can you find the helium bubble? Like, look as you might, you won't be able to find it. Is it that we forgot to put it in, or is it that the abundance in human beings, it's so small that it's a point that doesn't have any extent? We wouldn't see it on the chart. So it's a good data visualization. It makes us question something, and it solidifies our understanding. Oh yes, I remember helium is actually something that was only found in the sun at the natural, as a natural source. So we had to manufacture helium on Earth in order to have access to it. In which case it makes sense that it would not be actually found in human beings. It's not part of the human formula, so to speak. And there's other questions like lithium. Lithium is pretty abundant in the Earth's crust. We should be able to find it, but it's not there because it's not abundant in human beings. Other things like aluminum, at first you're like, why we don't have aluminum? It's just, no, it's somewhere else. You just need to go and find it. It's not easy to find. So if you can't find it at a first glance, if you have to trigger your attentive processes, it makes you really understand, or make sure you understand the data set, the context. These are good data visualizations. There's a few other issues with this chart. There's a bubble here which hasn't been labeled. That's problematic. It's using log scales, which is good. So there's log scales on the horizontal vertical thing, but the abundance doesn't seem to be logarithmic. At least it doesn't as easily follow a logarithmic pattern in our eyes, because here we're using the area of the bubble to represent something. There's insights we can get from this as well, which is sort of interesting. Is it surprising that the big bubbles are in the top right corner and the small bubbles, such as it is, are in the bottom left corner? And you think about this for a bit, and you're like, it isn't surprising, right? If you're in the top right corner, it means that you're both abundant in the universe and abundant in the Earth's crust. And so it would be surprising if it wasn't also abundant in human beings. As we live on the Earth, we've evolved on the Earth, and the Earth is part of the universe. At the same time, things that are not very abundant in the universe and abundant in the Earth's crust are unlikely to be very abundant in human beings. And that makes sense. Of course, there are specific elements that, buck the trend. Helium, for instance, should be there somewhere. It's the second most common element in the universe. Should be here somewhere, but it's only found in stars. And so we're not seeing the bubble. So I like a chart like this. It allows me to solidify my understanding about, well, in this case, the universe, or the chemical composition of the universe. Okay? These are the types of charts and the types of insights I want you to discuss. I'm not interested in seeing p-values. I'm not interested in seeing correlation coefficients that are listed to the 15th decimal. It doesn't work with my multiple I framework. At least for the data visualization component of this course. But even in the other modules, on the one hand, you have to be technically proficient. You have to be able to compute the p-values. You have to be able to come up with a correlation to 15 decimal places. But this isn't something you report on. So what I'm really looking for with this multiple I framework, if you're new to the class, it's in the general channel, you can see it there. What I'm really looking for is for you to be able to say something meaningful about what you're producing, rather than just showing me tables. It's not that I don't care about the tables or the numbers, but that's not what I want you to work on. Okay? Other types of diagrams exist. You have your network diagrams. The network diagrams are often used to try to really hint at a causal relationship. Now, it's going to be difficult to not see causal relationships in these types of diagrams, especially if we have arrows in the diagrams. So if your diagram is not a causal diagram, it's important to indicate that, to not give people the opportunity to make a mistake. Another approach which is really useful to help you draw insights is the approach of small multiples. If you're familiar with ggplot2, this is what's called a facet. And you take a categorical variable or a numerical variable or some variable that has a discrete number of levels. In this case, we have years for elections. So every 4 years we have a new presidential election in the States from 1952 to 2012. We produce a chart. It could be a choropleth, a heat map for geographical regions. It could be a scatter plot. It could be a network diagram. It could be a bubble chart. It could be a histogram. It could be everything. And for each of the years or for each of the levels of our variable, we produce the same chart. What I mean by that is we build a chart from a different data set, but we'll filter the data set so that it only contains the observations for that specific level, and we feed that into the same algorithm. And then we can compare what happens from one region to the next, from 1 year to the next, from one, you name it, group of individuals to the next. And that allows us to make comparisons between various groups. Small multiples, small means, well, you probably don't want to do this if you have 300 different groups. Right? If I have an array of 300 maps, it's too complicated to tell these things apart. 16, I can put it in a 4x4. That's something that's manageable. Small multiples, big way to get insights out of your data and your visualizations. Animation, I've mentioned a little bit about taking snapshots over time and then stitching them together. Rather than having a small multiple, you might decide that you want to make a movie of these and just see them pass over time. The problem with this is that you can't control necessarily the rate of animation. Or you might want to be able to compare 1952 directly with 1992. And if it's part of a static animation, a movie that's been made, you have to wait until all the years pass until you pause and you can get back, and well, that's not always going to be useful. There's a danger that if you only ever use certain types of visualization techniques, the kinds of questions that are well suited to these techniques, that can be answered by these techniques, will become the only types of questions we want to ask. And if these types of questions dominate the landscape, well, they're going to affect the type of data that we collect and how we collect it. And that's going to affect the future interests, and, well, then we've come into a cycle where we become too used to specific things. There is some value in exploring data, trying different methods, trying random methods. Trying something even if you don't think it's going to give you something useful. And publishing something, even if it's not the best ones, the best